Have you ever wondered if it's possible to walk through walls? It sounds absurd, right? But in the quantum world, this seemingly impossible act happens, and it's called quantum tunneling. Picture a ball rolling towards a hill. In the classical world, if the ball doesn't have enough energy to climb over the hill, it's not going to make it to the other side. The hill in this instance represents a barrier. But quantum particles like electrons don't always play by these rules. Even if an electron doesn't have enough energy to surmount a barrier, there's still a chance it can appear on the other side. This defies everything we've come to understand about the physical world from our everyday experiences. It's as if the ball simply vanished on one side of the hill and reappeared on the other. So in the quantum world, a particle can make it to the other side of a barrier without having enough energy to overcome it. Sounds intriguing, doesn't it? Now you might be asking, how does quantum tunneling work? It's all about the wave-particle duality and probabilities. Let's step back a moment and revisit a fundamental concept of quantum mechanics. Particles are also waves. This is known as wave-particle duality, and this duality means that the position of a particle isn't precisely defined. Instead, it's described by something called a wave function. This wave function represents a probability distribution. Essentially, it is a mathematical expression that tells us the likelihood of finding a particle in any given position. Now, let's bring back our barrier. Remember our ball and hill analogy from classical physics? If the ball doesn't have enough energy to climb over the hill, it won't make it to the other side. But in the quantum world, things don't work quite the same way. In quantum physics, the wave function of a particle, let's take our electron again, extends into and even beyond the barrier. This means there's a non-zero probability the electron can be found on the other side, even if it seemingly doesn't have enough energy to get there. This is where the magic of quantum tunneling happens. However, not all barriers are created equal. The probability of tunneling decreases with both the thickness and the height of the barrier. The thicker and taller the barrier, the lower the chances of quantum tunneling occurring. But here's the catch, it's never zero. The wave function decays exponentially inside the barrier, but if the barrier is thin enough, the wave function on the other side can still be significant. This means that even if the odds seem incredibly small, there's still a chance for our electron to tunnel through the barrier and appear on the other side. So even though the odds might be minuscule, there's always a chance for particles to tunnel through barriers, defying the laws of classical physics. Quantum tunneling isn't just a fascinating theoretical concept, it's embedded in the technology we use every day, and it fuels the stars in our universe. Let's take a closer look at how this quantum quirk manifests in our everyday reality. Firstly, we see quantum tunneling at work in semiconductor devices. Components such as tunnel diodes and transistors rely on this phenomenon to function. These are vital parts of many of the electronic devices we use daily, from computers to smartphones. Without quantum tunneling, these devices would not work as efficiently as they do, if at all. Moving from the microcosm of our devices to the macrocosm of the universe, we find quantum tunneling playing a crucial role in nuclear fusion. This process, which powers the sun and other stars, involves atomic nuclei overcoming the electrostatic repulsion between them. They achieve this through tunneling, which allows them to fuse together. Without quantum tunneling, the stars wouldn't shine, and life as we know it would not exist. Closer to home, we use quantum tunneling in scientific research. The scanning tunneling microscope, or STM, operates based on this principle. The STM can image surfaces at the atomic level by measuring the tunneling current that flows between a sharp tip and the surface being imaged. This gives us incredibly detailed pictures of atomic and molecular structures, enhancing our understanding of the world at the smallest scales. Finally, quantum tunneling has a significant impact on various biological processes. Some enzymes exploit this phenomenon to accelerate biochemical reactions that would otherwise be too slow under classical conditions. For instance, the process by which hydrogen atoms are transferred between molecules in cells involves tunneling. This affects how biological systems function at a molecular level. Quantum tunneling, a seemingly bizarre phenomenon, has profound impacts on our world, from powering stars to enabling the functionality of modern technology. It truly is a marvel of the quantum world.